That's very bad.
I like that I am recording how noisy you guys are for all posterity on YouTube. So every one of the videos looks like this is the most engaged class that has ever existed. So y'all are making me look good. Okay, so today the plan is that we are going to have a quiz, I guess, at the end. But for the first part, we finally arrived at the theory of integration. So we're not gonna be able to get through all of it, of course, but we're gonna start the idea of integration today. And this is a place where, if it's been a while since you've taken Calculus 4 or Math 304, which is the vector analysis class that I taught last quarter, I guess, then some of this stuff may be like a little rusty. But the ideas that we're going to be using to set this up are largely ideas that come from Calculus 4. So they're ideas of two-variable calculus. So the big problem with trying to define the notion of integration in complex, or for functions of complex variables, is complex functions take two real dimensional inputs and produce two real dimensional outputs, right? So you're working with a problem that is somehow intrinsically four-dimensional, right? Four real dimensional. If you think about f of z as being equal to f of x plus iy, but that's also equal to u of xy plus iv of xy. It's like you have two things going in, the x and the y, and then two functions coming out, u and v. So the way that you would think about this if you were doing, say, a vector analysis class or Calculus 4 is that f is a function from R2 to R2. It's a vector function. So when Cauchy was first thinking about this in the 1820s, one of the things that he cooked up, I mean, he was only like 22. What are we doing, right? He's like inventing complex analysis when he's 22 years old. Basically, he had to reduce the problem to something that was tractable. And the way that you reduce a high-dimensional problem to a lower-dimensional problem is you cheat and say, well, I'm not going to define integration from R2 into R2. I'm going to define integration from R into R2 instead, right? So he set this all up in the context of line integrals, right? So a line integral reduces the problem from one where you're somehow trying to take areas to areas, and instead you have some line, some path in R2 or in the complex plane, and that maps into the graph of that is a one-dimensional path, right? One-dimensional input produces one-dimensional output under one of these functions. So the setup for this is going to be parametrized curves. So essentially, complex integration, at least the version of it that we're going to do in here, complex integration is path integration. Or I guess the term for it is line integration from Calculus 2 or Calculus 4. From, say, multivariable calculus. Multivariable calculus. And when you do multivariable calculus, one of the things you do is you put all kinds of conditions on the curves that you admit and the domains that those curves can live in. And so that's what we're going to start with. We're going to build up a family of curves that we're allowed to use as the inputs for our integrals. So we'll start with a definition here. A smooth curve. Okay, actually, before I go on with this, there's this contest in mathematics for words that have the most meanings. Like, for example, normal has like 14 different definitions depending on which subject you're taking. Smooth is one that means whatever the person telling you that something is smooth means it to mean. Sometimes it means C1, sometimes it means Cn, sometimes it means C infinity, sometimes it means piecewise C infinity, sometimes it means analytic. For us, a smooth curve is going to be a differentiable curve. So C1 is what we're going to call a smooth curve. So smooth curve or differentiable curve is the graph x plus iy sitting in the complex plane of parametric function x of t, x is equal to x of t, comma, y is equal to y of t, and then where we set some sort of domain boundaries on our inputs. And we want x of t and y of t to be C1. X of t and y of t are class C1, so continuously differentiable. The reason we want to do that is because we're going to do that thing where we take z is equal to a function and dz is equal to something else, dt. dz doesn't make any sense unless these are differentiable and continuously differentiable. So what we're going to do is we're going to define complex integration by composition with a parametrized curve. So, for example, here's some examples. Like, suppose that I've got the function, well, let's actually take a look at what this does. So suppose I set z of t to be equal to z naught plus t times z1 minus z naught. And suppose t runs from 0 to 1, where z naught and z1 are complex numbers. Z naught in the complex plane, and here's z1 in the complex plane. Those of you that have recently taken or taught or tutored or TA'd or graded or calculus 4 or vector calculus should recognize immediately what this is, because if I put vectors instead of numbers there, it would be obvious what this was. So what is that? What kind of function? It's a straight line path. This is the standard parametric form of a straight line from vector calculus, right? This is the straight line path that when you put in 0, it cancels this term and you start at z naught. And then you move along the line until you get t equals 1. And if you put in t equals 1 here, you get z1 minus z naught plus z naught, which is z1. So this is just the old parametrized line that starts at z0 and goes to z1. Z of 0 is equal to z1, or z naught, and z of 1 is equal to z1. This is a nice one to remember because oftentimes it's nice to construct a linear path. I mean, why is it a line? That's a good question. I say it's a line. Why is it a line? If I think of this as vectors, why is this a line? I mean, tell me why it's a line?
Because you scaled both components simultaneously in the same ratio.
Well, I would actually think about z1 minus, okay, go ahead.
It's linear.
Okay, so linear turns out to be one of those words that has lots of different definitions depending on what context you use it in. So yes, it is linear because it's a line. The way to think about this is, you should think about this as the vector that points from z0 to z1, right? And this is like the anchor point. It's okay to think about complex numbers as being equivalent to vectors in R2, right? That's an analogy that we want to be able to do, right? So this starts us in R2 somewhere is one way of thinking about this. If you like, you can think about this as the vector xy, and then we're taking the vector, x naught, y naught. We're taking the vector x1 minus x naught, comma, y1 minus y naught. Why is it a vector? Because it's a difference of 2 points. And we're scaling it by t, where originally we have no scaling, so the vector is pointing nowhere. And as we increase t, it's like we're starting here and then adding on this vector that stretches out until it touches z1. That's an okay way to think about complex numbers and sort of when we're working with parametric curves, right? Analogy you already have available. Okay, well, we already talked about circles a little bit. So one way of thinking about parametric equations for circles is we could set up x of t is equal to x naught plus r cosine t, and y of t is equal to y naught plus r sine t. There's an old school parameterization from your multivariable calculus days. If you put this together as z of t, if you think about it as vector form, as x of t, y of t, then it's the familiar x naught plus r cosine t. Those of you that remember your calculus 4 are probably sick to death of this kind of function. And then if you put it into the x plus iy structure, this picks up an I, and you end up with x naught plus iy naught. And then over here, you get r cosine t plus I sine t, r, oh my god, I'm trying to do too many steps at the same time, plus r cosine t plus ri sine t. And at this point, you should be well developed enough to see that if you ever see cosine plus I sine t, you should just immediately think, oh, it's the complex exponential. It showed up. This is z naught plus r times e to the it, which is the one I did last time. Because cosine plus I sine t is equal to r e to the it. Okay? Okay. So, oh, and if I want the whole circle, I should probably tell you what the domain of the function is, right? There. Okay. So now let's talk about what
Is it
huh?
inclusive on both sides?
It doesn't matter. If I want to have if I really want this thing to be single valued, I can do this. But remember, we're going to be putting this into integrals, and integrals don't care about the value of functions at single points, right? So it doesn't actually matter if we overlap or not, as long as we overlap is just at one point. So I tend to think of the domain as being inclusive on both ends, but in practice it doesn't matter much. And normally we're doing this, where if it matters, it will matter because we're working across the branch cut. Okay, so questions about parametric curves? That should be pretty familiar, probably from ancient memory. A newer idea might be, or like a more recently forgotten idea. I'm not making fun of you. I immediately forgot every idea I ever learned as soon as I was out of the class I learned it in. So the contour integral. Contour is just the complex analysis word for a line or path integral. So the contour integral of a complex function f of z over a smooth curve C is defined by the integral over C of f of z dz is equal to the integral from a to b of f of z of t times z prime of t dt. This is just the standard definition of a path integral from calculus 4. And then if you want to blow it out into its complex bits, we think of it as the integral from a to b of f of x of t plus I y of t times x prime of t plus I y prime of t dt. And the reason to think about it like this, to think about these functions blown into pieces like this, is that oftentimes what we're going to be doing is pulling these functions apart into their real and imaginary pieces, because then we can use the theory of real calculus on them. If I work on just the real parts, or sorry, the real and imaginary parts, and I just treat the I like a constant, I can always factor an I out of an integral as a constant, and then just work directly with real integrals. It's a standard trick when we're doing the theory of integration of complex variables. This is okay? And then the one thing I left out here is that this setup depends on the following, where z of t is a smooth parametrization of the curve C. Remember, the curve can have more than one parameterization, right? There's more than one way to parameterize a curve. Okay. So we're going to start with the clunkiest possible way of defining what it means to do integration here, and then we're going to build up the theory. So we're just going to do raw parameterization at the beginning, and then after that we're going to discover that there's a fundamental theorem of calculus that works here. And the reason there's a fundamental theorem of calculus is going to turn out to be that really secretly in the background these are conservative vector fields. Okay. So, example. Integrate f of z is equal to z plus 1 over the straight line from z is equal to I to z is equal to 1. So if you're resistant to drawing pictures, you're gonna really hate the next part of this class because this is gonna be all about drawing pictures of contours, right? So it's much easier to do these questions if you have some idea of what it is that you're integrating over, right? What is the behavior of the contour that you're integrating over? So we're starting at the point z is equal to I, and we're integrating down to the point z is equal to 1. And for now, we should imagine that direction matters. In fact, direction matters in real integration as well, right? The integral from b to a is the opposite of the integral from a to b. So if I want to do a parameter or a contour integral, I need some sort of parameterization of this line, right? So this is our curve C. And by the thing we just did earlier, this should the easiest parameterization of that is going to be z of t is equal to z naught, the starting point, plus t times the finish point minus the initial point, where t runs between 0 and 1. So that parameterizes the curve. You can check real quick to make sure that you've got it right by plugging in 0 or 1 at least. Good habit to be in. Z of 0 kills all this and you get I. Z of 1 gets you 1 minus I plus I, which lands you at the right spot. This is the correct parameterization of the curve. So if I want to perform the integral, I just follow the formula, and as like sort of big and complicated as this looks, this is something that you've done lots of times in your life. This is U substitution, essentially. So, if z is equal to I plus t times 1 minus I, then dz is equal to, you just take derivatives. Right, regular old z derivative, or t derivatives here, because you're trying to put things in terms, if you like, dz dt. dz dt is 1 minus I, and so in infinitesimal form, that means dz is equal to 1 minus I dt. You don't actually need to include this stuff, but it helps make people feel less hand-wavy if you include this sometimes, if you don't believe in differentials. Okay. So we have z, and we have dz, and we know our a and b values from this. So the integral over the curve of our function z plus 1 dz is equal to the integral from 0 to 1. Replace all the z's with what z is equal to, I plus t times 1 minus I. And the dz with what it is equal to in terms of function of t, 1 minus I dt. And notice that despite the inclusion of the i's, we now have a one parameter real. Did I miss something? People looking confused. What did I do wrong?
Plus
It is.
Let's see.
What?
That was good.
Did I do something backwards?
I think you did great. It's fun.
You guys are making me feel nervous up here.
You're integrating the c plus 1, not just z.
Oh, yeah.
Oh. Yes, there. Z plus 1. Let me fix that. All right. Yeah, sorry, there's a plus 1 here I forgot to pick up. So this is z. So z is I plus t times 1 minus I. And then I'm going to add 1 to that because this is z plus 1. So thank you for the looks of confusion in that case. And for the people who just directly supported me, thank you for trusting that I did nothing wrong, even though I did. Now you just have a whole mess of complex arithmetic to do. I'm sorry.
Just separate. Right?
Yeah, but you know the way a calculus, a complex analysis professor makes this problem irritating? Express your answer in A plus IB form. Would I do that to you? I don't want to multiply this out. I'm just going to tell you what the answer is. So, what do you do now? You multiply everything out. So that's just complex arithmetic, and what you end up with after you do that is this. 2 minus 2it dt. I'm allowed to do that. Yep.
If you were to do it out on the board, would you think that it would be more efficient to convert to polar form first?
That's a good question. So the problem is that polar form tends to fall apart when you have addition involved, right?
Right.
So you can sort of work equivalently in polar and non-polar form. The problem is at the end you're going to have to sort it back into complex and like real and imaginary parts to do at least to properly do the integration. So it's up to you if you want to wrestle with the sines and cosines, basically.
No.
So, in which case, just do the algebra, right? So at least for this, I think my inclination would be to tell you just like do the multiplication out. Or if you like, distribute this to each one of these two terms and notice that like, you know, when you do that, there's like going to be a t term and a constant term, collect them separately and then, you know, without doing the algebra, which just means you're making me read a giant pile of parentheses with complex numbers inside. And then you integrate like normal. Because this is just a regular old integral. If you don't believe me, see, what you want to do here, this is totally unjustified. What you want to do here is you want to write that this is equal to 2t minus 2it squared over 2, all evaluated from 0 to 1. That's what you want to do, right? Because you just integrate term by term like normal. Now, why is that unjustified? Well, because we never defined anything with complex numbers inside of it. So what you do is, you say, oh no, secretly I didn't do that. I didn't integrate term by term. What I did secretly was I did the integral from 0 to 1 of 2 dt, and then I added that to I times the integral from 0 to 1 of minus 2 times t dt. And since that integral is a real integral, it's well defined. And since I snuck the I out, that's a real integral, and so I could just use the fundamental theorem of calculus. And so obviously I could have just integrated term by term. Now, do I care if you do this? No. You can always, this is one of these places where you can just assert, you can sort this out into real integrals and factor the i's out, which means you can apply the techniques of real calculus once you get to this point. So you can just integrate it term by term. I'm not trying to confuse anybody, but there is an issue here, right? The issue is we have not, the real calculus, how does real calculus work with an I running around inside? And the answer is because we didn't do it with the I inside, we just stuck it back in after we were done integrating. And there's the answer. Okay, so now I got a question for you. What on earth does that answer mean? What does that mean? How could I possibly interpret what that means? 2 minus I? So I integrated over this line. I've got some crazy complex function called z plus 1, and I restricted it down to this line segment, and the value that fell out the other side is 2 minus I.
Area under the curve?
Clearly. All right, so we're going to leave this as a lingering question. So, lingering question. What does this mean? Okay. Now, from a mechanical standpoint, this should be pretty straightforward, right? What did we really do here? We just built ourselves a U substitution and we plugged it in and integrated. That's literally all we did, right? Now, these get quite a bit more obnoxious when the functions get more complicated, right? Like, it's not always straightforward how to do this. And you can imagine if the functions say, well, I put like a cubic polynomial in here. You have to multiply out some cubic polynomial of the parameterized function, and there's just pieces running all over the place. Like, it sure would be nice. It sure would be nice if instead I could have just found an antiderivative for this thing and then plugged in the beginning and end points of the function, right? That's what the fundamental theorem of calculus tells you. The fundamental theorem of calculus for line integrals, which you learned in calculus 4, says if you have nice enough conditions on the functions, that integrating a function over a line is the same as a value. If you have what's called path-independent integrals, then you can stick the initial point into the function and the end point into the function and subtract. That's the fundamental theorem of calculus for line integrals. So that we're going to get there, but you're still going to be required to do some obnoxious parameterized integrals because you gotta earn your way to the good stuff. Although really what we're going to do is we're going to start immediately building what we need to have a fundamental theorem. So what we'd like, I'm going to formalize this, what we want really is we'd like to be able to say this. This is the golden goal here would be if we could say, I don't know, maybe there's an antiderivative, which we haven't defined. There's an antiderivative of z plus 1, and maybe it's equal to z squared over 2 plus z. So maybe there's an antiderivative of z plus 1, which is equal to this. And maybe what I could do is maybe the integral over the curve of z plus 1 dz, because this is a curve integral, if these happens to be path-independent line integrals, maybe we could say that this was z squared over 2 plus z, evaluated from I to 1. Z is equal to I to 1. Maybe I can get away with not referring to the parameterization at all, right? If I'm lucky, maybe I can say, it didn't matter how I got from here to here. This was at I, this was at 1. Maybe I can just use something like a fundamental theorem of calculus to just do it directly without referring to the parameterization that I used. Because parameterizations are useful, but obnoxious. So that's what we're going to try to do, is we're going to try to say when we can do this, when we can act like we do in calculus 2. Yep?
So path independence is dependent on conservative vector fields, right?
Yes.
Okay.
But it turns out analytic functions, because they're built out of harmonic functions, are actually secretly like conservative vector fields, which means they respect path independence. That's the sort of big picture. Okay. So we got to start classifying the curves we're allowed to have and the domains that they sit inside of. Okay. So let's start with an object called a simple closed curve. Okay. Anybody know simple? Oh, you guys have had topology. What is a simple curve? I mean, that's pretty simple, but from the mathematical definition is simple.
I remember in Calc 4 we talked about x simple, y simple regions.
Okay. It's not quite like that. That has to do with the boundaries of the regions.
Okay.
So simple means a curve is simple if it's non-self-intersecting. So this is a simple curve, and this isn't. So self-intersecting curves have trouble because there's ambiguity in what happens, which direction you head at a particular point. Okay? So simple curves do not self-intersect, and anything that does is not simple. Closed just means that the end is equal to the beginning. Oh man, I think I'm going to have time just to state my favorite ridiculous theorem in complex analysis. Okay. All right, so a closed curve has the same beginning as end in a parameterization, right? So if you think about it as a parameterized curve, wherever we start, we end. So this is a closed curve. In fact, this is closed and simple. This is closed and not simple. And then those curves over there are not closed. Okay? So Closed simple curves come with something called an orientation. So when we travel around a closed simple curve, we always want to travel, okay, so before I say that, I'm going to refer to the inside and outside of this curve. Now you may not know this, but referring to the inside and outside of a curve is one of the most dangerous things you can do in math. And in fact, the proof that a curve that is simple and closed has an inside and an outside is incredibly difficult to prove. Incredibly difficult. So I'm going to state an incredibly powerful theorem of abstract topology called the Jordan curve theorem. The Jordan curve theorem. So there's this old maxim in mathematics that some theorems have elegantly simple statements and absurdly difficult proofs, and other theorems have incredibly sophisticated other theorems have incredibly sophisticated statements and very easy proofs. This is in the first camp. So the Jordan curve theorem says this: every simple closed curve has an inside and an outside. That's a major theorem of topology, but that's true. Of course, by inside and outside, what you mean is that it divides the plane into two components, one of which it contains infinity. So there's a bounded component and an unbounded component. Okay? This theorem, if you want to prove this, and you take our topology sequence here, you might be able to prove it in the second quarter of graduate topology. So this right here, this little itty-bitty idea that curves can be divided into inside and outside is a major theorem in complex analysis. It was an accomplishment to prove that was true. So you got to be careful about those really easy statements. So now that we know that curves have insides and outsides because of the Jordan curve theorem, I can refer to orientations of simple closed curves. So if I talk about an oriented simple closed curve, in fact, we'll say positively oriented, what I mean is that the parameterization, if I think about the parameterization as describing the motion of a particle, the inside of the curve, the convention is for us is that positive orientation means the inside of the curve is always to the left. So I mean, if I'm traveling around the curve, and this is my point z of t, that the inside, this is the inside, but the inside of the curve is to the left of the direction of motion. You might have seen this if you did the geometry of curves in 3 dimensions. You see ideas like this too, right? So this is a positively oriented parameterization because as we travel around, we're to the left. Okay. A positive orientation of a more complicated curve might look something. So let's do another simple closed curve. So I could do this kind of thing shows up in complex analysis. I've got one curve and another curve inside of it. And then I can build a curve where I imagine I'm going in and out on the same line. Or actually, let's do it like this. Let's cut a little piece in here like this. And what we should notice is that for positive orientation here, on the outside we travel this way, but on the inside we reverse the direction that we're traveling. Because again, the idea is that as I traverse the curve, even if the curve is broken into pieces, anywhere on the curve as I travel, the inside of the curve is to the left of the direction that the particle is moving as it traverses the path. These are all rigorous. You can make this rigorous with tangents and normals and binormals if you want. Yep.
Can you define a curve to be an annulus, or is that too tricky?
So the way that the trick with an annulus is this trick. What you do is you say, okay, we're going to make a curve out of 3 pieces, C1, C2, and then I put C3 and C4 on the same line, and then I imagine travel around C1 until I get to curve C3, cut in on this line, do the inside part of the annulus, cut back out on C4 and get back out here. And so this is a typical approach to parameterizing a path that surrounds an entire annulus.
inside of C2?
This direction. Because you're trapped to the left of C2, right? You come in, it's this picture but sort of limited where you take those pieces and you kind of bring them together. These are good questions because this art of drawing these sort of piecewise chunks that parameterize a path, this is one of the things we're going to be doing all through the study of integration, is exactly this sort of idea. And it turns out that annuli are the next natural domain after circles that we'll talk about. All right, so that'll be the subject of Laurent series, which are like Taylor series on steroids. Okay, so that's all I can cover today. I'm glad that at least I got to state the Jordan curve theorem, the most wonderful theorem in the entire world. That's up there with the Harry Ball theorem on my list of amusing theorems. Yep. I'll say the primary. Capital L will always be the primary. Yeah. Yes.
Can I show you the homework?
Oh, I'm not. Sure.
There is no document.
Sweet.